We are very pleased to welcome Dan Spracklin here, the CEO of SoMax, a company that is developing its business in what we now call the circular economy. And actually, Dan has a background in business optimization, so that fits him very well to identify ways to help us make our economy more circular. And more specifically, he's working in a number of bioproducts areas, including bioenergy, clean water, nutrition, and combines process development, supply chain issues, and then trying to hook up with producers of waste, generators of waste, especially with universities in the Philadelphia area. And Dan, as I said, is the CEO of the company. He and his wife own this company now for what, 13 years now?
6 years.
Okay.
In 2013.
And with that, I will turn it over to Dan. He will share with us his experience in this.
Thank you for that introduction. And good afternoon, everyone. Let's say I'm very happy to be here. Currently, it's snowing. We're getting 5 inches of snow in Philadelphia, so probably happier than most presenters to be here. Just a little bit more on my background. So I was 15 years in corporate America in process improvement, process optimization in the financial services and in insurance companies. So that goes to show you that you can apply sustainability to everything. You can come out of IT and insurance, as I did, and then find yourself in a waste company. So we bought my wife's family business is a company called Gray Brothers Septic Services. It was started in 1929, so we're now celebrating our 90th year. In industries like waste, there's always business. Right? We're always going to have waste. So that's what attracted me to the industry. And once I got in, I realized how wasteful it actually is. So I had a crazy idea of starting to look at the materials that we're hauling, greases from industrial food manufacturers, and saying, this isn't waste, this is a resource. And how do we efficiently manage those resources? So you won't hear me talk about waste a lot. You'll hear me talk about organic resources. And that's really what we're trying to do, is better manage those organic resources, not only within cities, but this can be applied globally as well. We try to focus on the core human problems, the core human functions. So in here we're talking about organic resources that are derived from sewage sludge, from biosolids, from food waste, and from agricultural waste, and turning that into fresh produce. So what's more human than eating and going to the bathroom, right? It's one unique common denominator that we all face. I read my 3-year-old daughter a book every night called Everybody Poops. And it really applies here. So we have very much an infinite supply of material in order to upgrade and process into new materials. So in essence, what we're trying to do is to develop what we call the closed-loop food production. And this is turning a one-way linear food system that we have today into a smaller, hyper-local, circular food system that develops products from existing waste. And we're working really to close loops in water, nutrients, and energy. So let's look at our current food system. So we have a very linear current food system. This graph is from the Ellen MacArthur Foundation. It's from their latest report that was presented in Davos last month. And it is showing the amount of waste, the amount of food produced globally at 7.1 billion tons. 4.3 is for human consumption. 2.9 billion tons of food is destined for cities globally. And if you follow this through, you can see that 2.4 is eaten, 500 million tons is wasted. Then you have human waste of 2.3 billion tons. That gives us a market of 2.8 billion tons annually of material across the globe. So whether you're in Dubai or Dallas, you're in Stockholm, or you're in Stockton, California, this applies anywhere you have a massive humanity. Of that 2.8 billion tons, less than 2% of it is currently recycled. So what you end up with, and you look at all these inputs, you look at your fresh water, your fossil fuels, your chemicals, and your nutrients. All those are being concentrated in cities and then wasted, either through the wastewater treatment process or disposed of in landfills. So what we want to do is to repurpose those constituents, those elemental components of the food that we eat and of our waste, into products that go back into the environment and closing those loops. So a couple of good facts from this report are, for every dollar we spend on food, we spend $2 in social costs. Social costs include things like environmental damage, depletion of finite resources. A big one here, since we're in Florida, as an example, is phosphorus. Phosphorus is ubiquitous in the agricultural industry. It's required to grow produce, but we're actually looking at peak phosphorus and running out within the next 100 years. So how do we grow food without phosphorus? Well, we're going to have to recycle it. And the way that you recycle it is through things like urea in your urine. The human body is very poor at absorbing nutrients in food and keeping it for your growth. Approximately 87% of all the nutrients that you take in through your diet actually end up in your waste. So we're very inefficient human beings, and we leave a lot of waste behind, materials, and let's repurpose those. So what that does, that results in the environmental cost, the total cost for food production annually, globally, is $5.7 trillion. Think about that, $5.7 trillion we're spending every year to feed ourselves, because we're doing a very linear and inefficient fashion for food production. We have another component crisis, or a competing crisis, and that is landfill space. So in the Northeast, in Philadelphia, we have 10 years left of landfill capacity. And this is areas of the country, so you're talking about DC, New York, Boston, that's going to start sending all of their waste south to places like Alabama or Arkansas. There was a big kind of funny article and joke going on CNN this past summer that there was a train stuck outside a small town in Alabama. That train was filled with sewage sludge from northern Jersey and New York. And it was stuck there for 4 months because it was trying to get to a landfill in Alabama. So think about magnifying that impact across that geography, where 1/3 of the nation is actually sending us its waste down here. And what we're going to end up doing is filling up waste across the country. So up on the screen, you'll see there's a quote from Michael Hoffman. So Patel is a large waste industry in the Northeast. They operate in Vermont and in Massachusetts, and he's decrying this as an emergency, a crisis. If we don't solve something within 10 years, we get these negative feedback loops where we start to fill up landfill space. And what a waste to send, dispose of these nutrients from New York City or from Philadelphia and send them all the way to the West Coast, transport them just to be disposed of. You can imagine how many carbon emissions are associated with that supply chain, how much fossil fuels being consumed to move that material. So currently, there are 3 main ways to deal with organic waste or organic resources. The first one is composting. Compost has been around for hundreds of years. It's very efficient, or it's very inefficient. But it does end up making produce, so kudos to you that compost at home. Compost has a carbon efficiency rating. So carbon efficiency means how much carbon's in your base feedstock and how much carbon's in your end product. Composting has a carbon efficiency rating of 10%. So that means that 90% of that carbon is valorizing into CO2 or to methane, depending on how you're processing and handling that compost, whether you're windrowing it or you're doing static air piles. The second one, first one obviously is landfill. I skipped that one, but that's zero efficient. It's not a good place for organic resources. When you think about landfills, you think about all the problems associated with them. What do you think about? You think about leachate, which is leaching into our water supply and destroying our water supply. You think about methane. Those two problems are caused by having organic material in a landfill. You know, it's 2019. We've got to come up with a better way than digging a hole and throwing everything in the ground and covering it up. So the other process, which is very popular here, shout out to Professor Colhane in Solar Cities. We work very closely with one of his co-founders, but that's anaerobic digestion. Anaerobic digestion is a biological process that decomposes waste into methane. Its efficiency factor is 50%. It takes anywhere from 15 to 30 days to process that material into usable fuel, into biogas. That biogas can be upgraded and injected into a pipeline to meet the standards of natural gas, or it can be upgraded to vehicle fuel to run heavy vehicles as a diesel replacement, or it can be combusted for energy production. With that, you also have things like digestate that still has to be handled with it. So what do you do with the solids and the lignin that comes out of your anaerobic digestion? A lot of it's used for animal bedding, it's used for a soil amendment, has a lot of applications more in the developing world. China has something like 30,000 anaerobic digesters. Germany has 8,000 municipal scale anaerobic digesters. In the United States, we have a little over 1,100 municipal scale digesters. So we have the opportunity to have about 14,000 of these built, but the economics are difficult, the siting is difficult, and the policies are difficult to help prevent this. In fact, in the last 2 years, there's been zero growth in the anaerobic digestion deployment across the United States. So with that, what I'd like to do is introduce you to a new technology for biomass conversion, and that is Hydrothermal Carbonization, or HTC. HTC is the most efficient way of processing biomass into energy, or bioproducts. So we are 95% efficient, so only 5% of the carbon is getting lost in the process, and that's valorizing into CO2 during the HTC reaction. For us, depending on the feedstock coming in, we have a 30 minutes to a 4-hour retention time. So compare 30 minutes to 30 days. This is how much more efficient, how much more massive we can process material in a quicker and timely fashion. We also are able to get fertilizer and water out of this process. And we'll go into the process. Now, what I want to talk to you about is just, you'll see this slide a couple of times in the presentation. I'm going to take you through the entire loop. So what we do is I am a research sponsor. I sponsor 3 master's engineering students. I've sponsored research for the last 5 years at Villanova University. And we've developed this closed loop food production where we take food waste from Villanova, we run it through the HTC process to generate energy. We utilize that energy to grow produce, and then we sell that produce back to Villanova. So what is HTC, or hydrothermal carbonization? The easiest way to think about it is a industrial sized pressure cooker. We apply heat and pressure to organic material. This is done in an aqueous solution in a water solution, and that water acts as a catalyst because we're heating it up, the pressure is putting it into a subcritical state, and it goes in and it's leaving large chain carbohydrates into smaller chain hydrocarbons. This allows us to essentially recycle elements. So we're putting in manures, we're putting in biosolids, we're putting in food waste. We're going in and grabbing the carbon and hydrogen and putting that in the solid form. And then all the other water-soluble elements like nitrogen, potassium, are going into the liquid phase. And from that, we can then further extract those out. What happens is basically you put in this material, and the back end you're getting hydrochar. Hydrochar is a solid fuel. It is a carbon. The easiest way to think about it is to think about coal. So what HTC really does is it mimics the natural process of coal formation, applying heat and pressure to biomass. What takes Mother Nature 250 million years to do, we do again in 30 minutes to 4 hours. So it's a big factor of improvement on that process by applying mechanical engineering. So this is actually a picture of our reactor. This reactor will process 10,000 tons of biomass on an annual basis, and it is built on the standard 40-foot shipping container. So all this in a little package of a shipping container. You do have some ancillary equipment around it. You have tanks for storage, you have tanks for processing, presses and things, but the actual HTC unit itself is a standard shipping container. This modularity allows us to scale up. So if you wanted to process 100,000 tons, you just put 10 of these in parallel, you run a header, and now you can run 100,000 tons through these reactors, these 10 shipping containers. Above, what you see there is all the chemical reactions that occur. I won't go deep into the chemistry unless you guys have any questions after. So what we did is we produced a bunch of char feedstocks. We took a feasibility study, and what we did is we separated out and took each of the food. So we took dairy, we took carbohydrates, vegetable proteins, animal proteins, fruit, as well as anaerobic digestate. We ran it through our process, and this is the chars that you see out. I won't go into the details of each of them. What I like to do, I'm a big proponent of showing your failures as well as your successes. So you'll see a couple of failures in this presentation. A little bit of foreshadowing there. So what doesn't char? Brown grease, dairy, cheese is terrible. You'll get these gloppy messes. But when you go back to the mixed food, right? So if you mix grease, you mix dairy with carbohydrates, with fruit, with vegetables, it will actually convert into a char. You just can't do it on its own. So you couldn't set up this process at a rendering facility and just take animal fat and put it through. You'll just get gloppy mess after. But if you combine that with green waste, leaves, grass clippings, or even combine it with other food products, you could actually get a really nice char. So none of this worked. You're very disappointed. Our research labs smelled absolutely horrible. Our fellow researchers don't like this when we go and we take sewage sludge and we dry it out overnight, 24 hours. We come to the lab the next day, it stinks. So what else doesn't produce char? Paper, plastics. What this does, though, is actually produces a nice pellet. So if you look at this low density LDPE, for example, that's a nice little pellet that can be separated out from your char. So as long as you have minimal contamination with plastics and paper, it does not really affect the process. And it's easy to separate out. And this little guy here is actually a good fuel pellet for incineration plants. So our contamination we can modify and then actually sell to incineration plants because it has a lot of higher heating value. We're doing research right now, and we'll have pictures of the results of mixing in paper with food waste so that we can take the paper products. The other thing that I'm pushing towards this summer is to look at a sister of HTC, which is called Hydrothermal Carbonization, or VTC. Exact same operating conditions, but you take dry material and you inject steam into the reaction chamber. That steam, I believe, my hypothesis is will help break down the paper and the wax better. If we can accomplish that, then this takes on a whole other approach. It's not just food waste that we're going after, but think of all the waste coming out of every McDonald's, every Wendy's, every fast food place can be processed through this, if we're correct in our hypothesis. So we produce hydrochar. What is hydrochar? Again, it is a hydrocarbon in a solid state. It can be pelletized, it can be left as friable. But we're looking at, to commercialize this, we're looking at the energy industry, because renewable energy is the low-hanging fruit for us. There's always a demand, there's always a market for it. So here's how we can commercialize it rather quickly. And this is we take a page from IT development, from software development. This is our minimum viable product, MVP. You'll hear that a lot from the Steve Jobs and the Zuckerbergs of the world. So what it is solid fuel. And what you'll see here is, the blue is its higher heating value, or its heating value. So we have 23 megajoules per kilogram of energy value. That's the same as your mid-grade bitumous coal. So down here at Apollo Beach, there's a large coal-fired power plant. You could run that same plant off hydrochar. You just have to meet the volumes that it produces. If you were to say produce the 300 million tons of biosolids that are produced in New York State, for example, convert them to hydrochar, put them on a ship, and ship them down here to Florida to consume for energy. You can do that in existing infrastructure. You don't need to change the plant at all. It's currently scheduled to go under an upgrade to renewable natural gas, or to natural gas combustion rather than coal combustion. But the key here is in the orange and the green, you'll see the emissions factors for fossil fuel. And what you'll notice up there is hydrochar has 0 emissions. I want to be very clear though, we do have carbon dioxide emissions. We have CO2 emissions, but they're biogenic in nature. So we are carbon neutral. Our saying CO2 emissions are equivalent to everyone exhaling across the globe. Or think of a forest that in the spring it's growing leaves and it's soaking up a tremendous amount of CO2. Those leaves fall and then it releases all that CO2 back in the atmosphere. This is respiration. These are naturally occurring CO2 emissions. They're not fossil fuels, so they're not additive to the climate issues. So we do have CO2 emissions, but we're considered renewable energy and carbon neutral. So what can we do with it beyond energy? We can do a lot of really cool things with it. We were having some discussions earlier about some advanced materials. I'll give you a couple examples. This one you have to wrap your mind around a little bit. You can take biosolids from a wastewater treatment plant, process that into hydrochar, activate that hydrochar either through chemical or physical activation, and now you have activated carbon. Activated carbon can be used for water and gas filtration. So you take biosolids and you clean your drinking water. It takes a little bit to get your mind around it, but this is what's possible here. We also can get into advanced materials. What our interest is really in the next phase of this is to turn it into, actually combine it into industries to increase our industrial symbiosis. So industrial symbiosis, when one waste stream is the input or feedstock of another industry. We like to process this hydrochar and use it in the concrete and use it to replace coal in the steelmaking industry. If we were able to accomplish that, we would have the equivalent reduction of taking every single transportation sector emission off the plane. So you can either electrify every vehicle, every ship, every airplane, or you figure out cleaner ways to make steel, cleaner ways to make concrete. You have the same net effect. Some of the other ones to highlight is we have some advanced nanomaterials. So we can make things like carbon nanosheets. You start layering these together, and you actually have supercapacitors or ultracapacitors that are 25 times more efficient than lithium-ion batteries. So if you did want to go and electrify the transportation sector, here's a way to do it. And I'll give you a little dirty secret. Lithium-ion batteries require a couple of finite resources. The biggest one being cobalt. Now, cobalt is mined in conflict areas in West Africa. There's not enough cobalt on the planet to electrify the transportation sector. So as many Elon Musks as we have out there making great cars that run on electricity, we can't get there on our current lithium-ion batteries. We've got to find a replacement. So would it be great to take that banana peel, turn it into a supercapacitor, and store energy with it, rather than throwing it away? I use that example when people always remind me and accuse me of building Mr. Fusion from Back to the Future. That may be dated a little bit for this audience, but he's able to pour a beer in, put a banana peel in, and then throw the beer can in, and it gave his car enough energy to time travel. Theoretically, that works, except for the aluminum. The aluminum does nothing for you from an energy concept. So we've gone through the loop. We've converted all this material into Hypercharged. So in the HTC process, you have two product streams. You have the solid Hydrocharged stream, and you have liquid processed water. That is a nutrient-dense water. If you were to take that, it's high strength. You'd have to put it down the sewer as a high-strength waste because you have elevated BODs and CODs, biological oxygen demand and chemical oxygen demand in that processed water. So you can dilute that processed water 1-to-1, then you now have a liquid fertilizer. The problem with that is actually pinpointing your NPK values, because again, you're getting this from food waste. So one day you may get a shipment of bananas that's gone bad, or oranges that have gone bad, or milk, and the next day you're getting animal proteins, or you're getting vegetable proteins, and how do you homogenize that to get a nice NPK ratio? It's very difficult to do. So this is a low-value concentrate fertilizer. And you can sell it just like it is, or you can upgrade it. So the way we upgrade it is through a process called vacuum distillation. So it's your typical distillation process, but by adding pressure, we lower the temperature. So we're at 85 C. What happens is we separate it out. We're condensing down now all those nutrients into an actual pellet. That pellet can be bagged and sold to like Scott's Lawn Guard that you just throw on your lawn, or it could be used in the horticulture industry for aquatic soil amendments or soil amendments themselves. And then you're able to, with the addition of sulfuric acid, we're able to create ammonium sulfate. Ammonium sulfate is a market-ready nitrogen-based fertilizer. Its NPK value is 2100. It's all nitrogen. So from that, we're extracting out the nitrogen. Everything is left over in the concentrate. And then at the end of this process, we have distilled water. So we have clean water that can be reused for either industrial purposes, agricultural purposes, or actually upgraded into drinking water. So depending on where you put this in geography, this water may be the most important component of your bioproducts. So think about this in Gaza, or in the Middle East, or even in closer to home in Arizona, outside Phoenix, outside Scottsdale. You can help eliminate some of these droughts by creating water. And at a 10,000 ton basis, we're making quite a bit of water. So this is a mass and energy balance. We have to work on the slide. It's very busy, it's hard, but I'm going to try and walk you through it. So in the yellow are your inputs. In the red is your internal consumption. And then the green is your actual outputs. So with this, with 10,000 tons of food waste coming into the HC reactor, it goes through there, and we have the separation between the hydrocharged and the processed water. So from 10,000 tons, we get 15,000 tons of hypercharge. Well, we get nearly 8,000 tons